All right, we've been setting up and talking about how to describe equilibrium, and we've said that we're going to use that to, at least initially, talk about this issue of situations where vapor and liquid are in equilibrium with each other. And we need to do that if we're going to start thinking about describing separations operations. And we've already said that the key equilibrium criterion that we're going to be focusing on quite a bit is this idea that for each component in a mixture, equilibrium is obtained when the chemical potential of that component is equal or equivalent in all of the phases that are in equilibrium with one another. And so for the situation of vapor-liquid equilibrium, that corresponds to a situation where we're going to say the chemical potential of component I in the vapor is going to be equal to the chemical potential of component I in the liquid phase. And now we also have said that the chemical potential can be described as fugacity. So Lewis taught us about how to define fugacity relative to the chemical potential. So these two expressions are interchangeable. And so we're going to be focusing right now on this issue of the fact that at equilibrium, the fugacity of component I in the vapor phase is going to be equal to the fugacity of component I in the liquid phase. And so what we're going to do today is take that next step from this abstraction level of talking about chemical potential and fugacity and try to relate things back to measurables so that we can work with these relationships and use that as we go forward to solve vapor-liquid equilibrium problems. So we're going to be starting from the expression that we have here, the fugacities being equivalent across the phase boundary for component I in the situation where the system is in equilibrium. And so our first step is to think about what we need to do with these two terms. We only have two terms in the equation, and so we've got to start somewhere. And so perhaps the easiest one to deal with is to start by thinking about the vapor phase. And so if we think about the vapor phase, and we think back to your training in Thermo 1, this should be something that we're familiar with knowing how to do, right? So we know that for an ideal gas, the fugacity is simply equal to the partial pressure, right? And when we were talking about the Lewis description of fugacity, we said that in situations where we have a real gas, we can introduce a fugacity coefficient to describe that distinction. And so we're going to use that approach here and say that the fugacity of component I in the vapor phase can be expressed as some mole fraction y sub I multiplying a fugacity coefficient for component I and the total pressure of the system. Or another way of saying this would be the fugacity coefficient multiplies the partial pressure of component I in the system. And so the case where we have an ideal gas, the fugacity coefficient goes to unity, and we recover that the fugacity of an ideal gas is simply equal to the partial pressure of that particular gas in the mixture. And so the vapor phase, relatively straightforward at this point. At least we've gotten from fugacity now into things like mole fraction and pressure. Fugacity coefficient, maybe that's a little bit trickier, but we're familiar with the idea that there are equations of state out there that will give us the ability to calculate that fugacity coefficient. And so even though the math might be more difficult, we know there's a path forward to getting everything we need there, and that fugacity coefficient is going to depend on, at the very least, things like pressure, temperature, and volume, and perhaps also composition if we have a mixture where mixture effects are contributing to non-ideality. So the vapor phase, we've got that relatively well under control. The liquid phase, on the other hand, is a little bit more complicated, and that's where we'll be focusing our attention here today. Now, there are a couple different ways that we can approach this, and we're going to talk about one of them here. You'll see in some of the reading assignments that there are different approaches, but everywhere gets to the same end result. And so as you're doing the reading assignment and looking at this video and looking at your notes, I want everybody to be thinking about how all these different approaches take slightly different paths to get to ultimately the same end point, and then pick the version that works best for you in terms of internalizing what's going on here. So the way that we're going to do this is to use a parallel approach here to what we've talked about for the vapor phase. So remember, we said that if we think about having an ideal gas, right, then the fugacity of component I in the ideal gas mixture is simply equal to the partial pressure of that component in the mixture, right? Or we could write this out more explicitly in terms of the mole fraction, right? We could say y sub I times P, right? So in the ideal gas mixture, we have a mole fraction multiplying the pressure. That gives us the ideal gas fugacity. So we're going to do something similar here for the liquid phase. So we're going to say that the ideal solution fugacity is going to be given as a mole fraction in the liquid phase. But instead of multiplying the pressure, we're going to use the fugacity of pure component I in the liquid phase. All right, so this is a little bit different from what we've done for the vapor, but similar in the sense that we have a mole fraction multiplying something, and something that has units of pressure, of course, since we're dealing with fugacity. We'll come back and talk a little bit more about this at various points throughout the semester, but this is what's typically called the Lewis-Randall rule or the Lewis-Fugacity rule in the Prausnitz text. So you'll find this is equation 2-49 in the Prausnitz text. Be a little bit careful in that section. There are a couple typos in there, so see if you can spot those, or if you're unsure about what's a typo or not there, feel free to drop us a line and we'll help you sort that out. But anyhow, this Lewis-Randall rule is sort of the limiting case for liquids. It's a limiting case, much like the ideal gas as a limiting case for the vapor. And so, but most liquids are not necessarily ideal solutions. And so we have a situation where we need to deal with real solutions as well. And we're going to do something similar to what we've done for the vapor phase. So in the situation where we have a real solution, we're going to say that the liquid phase fugacity of component I is still the mole fraction of component I in the liquid. We're going to multiply it by now an activity coefficient. And we've still got our fugacity of pure component I in the liquid phase. All right, and we're going to come back and talk about this activity coefficient later in the semester, but this is functioning similarly to the fugacity coefficient in terms of what we've said about the vapor phase so far. The activity coefficient is simply going to describe the non-ideality that makes the solution real as opposed to an ideal solution. And we'll use models that are called activity models to calculate activity coefficients, which will be a similar idea, but different approach compared to using equations of state to calculate a fugacity coefficient. All right, so this is how we're gonna work this out. And so we could come in and say that now our equilibrium criterion is y sub I times the fugacity coefficient of I is equal to xi gamma I times f pure I in the liquid phase. All right, so this is just our equilibrium criterion now, one step closer to measurables. We at least see pressure in two different mole fractions in there. Again, y we're going to use as the mole fraction in the vapor phase, and x we'll use as the mole fraction in the liquid phase. And then these two terms that deal with non-ideality also in both phases. Problem is that we still have this fugacity of pure component I in the liquid phase. And so we need some way to zero in and think about what that fugacity is going to look like. And this is where the approaches deviate a little bit in terms of what you're going to see in the reading assignment versus what we're going to do here. But again, I'll ask you to take my word for it that we're all going to end up at the same place, and everything's going to be fine there. And so our next step in this process is to deal with F pure I in the liquid phase. And to simplify things a little bit here, I'm going to go ahead and drop the pure subscript as we go through this part of the discussion. That cleans things up a little bit, but want to make sure that everybody recognizes that at this point we're dealing with addressing or answering the question of how do we describe the fugacity of a particular component when it is in the pure liquid condition. And the way we're going to do this is we're going to set up a big identity. So we're just going to multiply by 1. And that's going to get us what we need. We're going to do this at some particular temperature. Remember, when Lewis set things up, we're talking about fugacity at a particular temperature, so we're assuming that is specified at this point. And so we're going to be thinking about answering the question, what is the fugacity of a liquid at a particular temperature, and how does that depend on pressure? And we're just going to, like I say, set up an identity here. And so we'll write that out and we'll come back and discuss this a little bit. So we've got the fugacity of component I in the vapor phase evaluated at the saturation vapor pressure of component I. Again, that saturation vapor pressure is going to be evaluated at the system temperature. Remember the Antoine equation or the Clausius-Clapeyron equation, right, gives us information about how the saturated vapor pressure depends on temperature. So we know that's going to be evaluated at the temperature of the system. Then we're going to multiply that by a second ratio. So the fugacity of component I in the liquid phase also evaluated at the saturation vapor pressure, divided by the fugacity component I in the vapor phase, evaluated at the saturation vapor pressure. And then our third ratio here is going to be the fugacity of component I in the liquid phase, evaluated at the system pressure, just P. And that's going to be divided by the liquid phase fugacity for component I evaluated at the saturated vapor pressure. And to complete the identity, we need to multiply by the saturated vapor pressure. So if you look at this, if we look at this big identity that we've written out, we see that everything cancels out, right? We end up with just 1 is equal to 1 if we cancel everything out here. So we haven't actually done anything, right? There's no assumptions here. There's nothing going on here other than just setting up a big identity. The benefit of this is that by structuring things in terms of these 3 ratios, we actually give ourselves the ability to simplify things out. And so we make the problem easier in a sense without having to actually do anything, which is a little bit weird, but it's going to work out nicely for us in terms of thinking about what we want to do moving forward. So we're going to deal with each of these 3 ratios. And so, if we sit and stare at this for a little while, we might start to see that some things make a certain amount of sense in terms of how we might go about simplifying things. For example, if we look at the first ratio here, we might recognize that we know that the fugacity of component I in the vapor phase at the saturated conditions is going to be equal to the fugacity coefficient at saturation conditions times the saturated vapor pressure, right? If we're at equilibrium and so the vapor is saturated with component I, then this relationship has to be true. And this means that this first relationship is simply equal to the fugacity coefficient of component I at saturation conditions at the system temperature that we're looking at. And so that's just coming out of the definition of the fugacity coefficient. So that works out relatively well. If we go ahead and look at the second term here, right, we've got a situation where the fugacity of component I in the vapor and liquid phases are given at the same condition, right, the same pressure. And so this, by the definition of equilibrium, goes to unity, right? Because if we're at equilibrium, then the fugacities in both phases for a given component have to be equal to one another, and the pressures are the same, so that term goes to unity. So the first 2 terms here, pretty straightforward. All we're going to end up with is this fugacity coefficient of component I at the saturation conditions. The third ratio is a little bit trickier to think about or deal with, and so we'll spend a little bit more time thinking about that, but I'll convince you that if we keep our fundamental equations in mind, that we'll be able to go through and work this out in terms of what's going on here. So to think a little bit more about this third ratio, we're going to come in and use some of the Lewis-based discussion that we've already gone over about the relationships between chemical potential, fugacity, and Gibbs free energy. So, all right, let's get into the third ratio here. All right, so we're just going to set out here before we begin to remind ourselves that all of these things, these terms are related. So Lewis gave us a relationship for fugacity relative to chemical potential. So we know that we've got that relationship for us. We also know that the chemical potential is the partial molar Gibbs free energy of component I. And here we have to remember that in this situation where we have a pure component I, then the partial molar Gibbs free energy simply becomes the Gibbs free energy of pure component I. And it's important to remember here, right, that we're dropping the pure subscript as we work through this part here, but we're talking about pure component I. And so all of this chemical potential and fugacity stuff, right, comes down to or can be extrapolated out to just pure, the Gibbs free energy of pure component I. And so what's helpful about that is it means that we can start to deal with this fugacity in terms of the Gibbs free energy. And I'll try to convince you here that that's actually something that we want to try to do, right? But what our goal here is to think about how we can get a relationship or an expression for this ratio of two fugacities at different pressures. Another way of saying this is that our goal in analyzing this third ratio is to answer the question, how does fugacity depend on pressure? Because we need an explanation for how the fugacity changes as we move from the saturation vapor pressure to the system pressure P in this system. And so the reality is that if we, sort of sit and stare at this for a while, we see that in this differential, right, we have an expression for the fugacity, and that's going to connect up to the Gibbs free energy through this whole relationship and the fact that we're thinking about the pure component I system here as we go through this analysis. And so all we have to do is do a little bit of integration to figure out this problem. And so if we go through and we integrate this out, we see that we'd end up with a situation where, let's see here, as we integrate, and we're going to integrate dg pure I is equal to RT d ln Fi, and this, I guess we'll bring the pures back in here to make this a little bit easier. And of course, we're talking here about the liquid phase as well, so we could put in liquid as well. So if we go through and we integrate that, right, we end up getting a situation where we get G pure I at system pressure minus G pure I at the saturation vapor pressure. We're integrating from the saturation vapor pressure to the system pressure. And this is going to be equal to RT times the natural log of F pure I evaluated at the system pressure divided by F pure I evaluated at the saturation vapor pressure. And of course, these are in the liquid phase. And voila, we see a situation here where we know we must be headed in the right direction because we see on the right-hand side that we're getting an expression that matches the third ratio that we're looking at. Now, that comes at the expense of the left-hand side, which is still in terms of Gibbs free energy, and maybe that doesn't look all too friendly at this point. But it turns out that that's something that we can work with here. And so what we're also going to do is we're going to recall our fundamental equation that we used with our discussion of Lewis, right? But dg is equal to v dp minus s dt. And at a given temperature, if we integrate that with respect to pressure, we find out that we get the same left-hand side, right? So we can do something like this. The left-hand side stays the same. And we end up with a situation where on the right-hand side, we have the integral from pi sat to the system pressure of, in this case, the molar volume of pure liquid I. It's being integrated as a function of pressure. Right, and so what's nice about this is now we can get rid of the left-hand side in terms of the Gibbs free energy, and we're pushing toward this idea where we have a situation where we're going to be able to get this third ratio in terms of measurable quantities that is going to be useful to us. And so if we take a look at that and we group everything together, we see that this third ratio looks like F pure I. And that's evaluated at the system pressure relative to same thing, evaluated at the saturation vapor pressure. And that's going to be equal to the exponential of 1 over RT. And we'll just carry this integral along with us. Now, often we're going to drop the pure subscript here from the volume, but keep in mind that as we're going through this, right, this is what we're talking about. We're talking about the pure component I molar volume in the liquid phase as we're doing this integral. And so this is our third ratio. And so here we have, change the color, but here we have our third ratio, and that third ratio is equal to what we're going to call the Poynting factor. All right, now in the Matsoukas text, this is going to be written out in the integrated form, and so you're going to see something that looks more like this. Just drop that pure subscript here. And so oftentimes you'll see the Poynting factor written out where the integral has been evaluated in a situation where either an average volume can be used over the pressure range of the integral, or where the system is considered incompressible, and so thus the molar volume of the pure liquid is pulled out of the integral. And often that's a very good approximation to make, particularly if the range of integration here is relatively small. So this is the third ratio that we're going to be talking about. Oftentimes the molar volume of the liquid is a weak function of pressure, so you can use the simplified version here, and that's what you see in the Matsoukas textbook. Turns out in a lot of cases the Poynting factor is going to be relatively close to unity for us. And so it turns out that if you look at the argument of the exponential here, that the ratio of V over RT in most cases is a relatively small number. So I'd encourage you to go and look up the molar volume of water just at room temperature and divide that by RT. and see what that looks like. It turns out RT is a relatively big number, and so that ratio ends up being pretty small. And so as long as the difference between P and PI sat is not enormous, the Poynting factor is often very close to unity because the argument of the exponential is very close to 0, or is it just a very small number. So I'd encourage you to take a look at that and see where that ends up being true. One of the cases where we'll come back to later in the course to see that that is not true are things where you're dealing with, for example, geologic pressures, right? If the pressure is just absolutely enormous, then the Poynting factor can play a role, and we can actually see that the Poynting factor tells us about, for example, how you convert carbon into diamond at extremely high pressures. So it's not, the Poynting factor can be useful in some cases, but in a lot of the situations we're going to be talking about here, we're going to find out that the Poynting factor is usually relatively close to unity. All right, so we collect everything back up and come back to our fugacity of component I in the liquid phase of our mixture. And so now we have a situation where, and take one step back here, pure component I in the liquid phase, right? This was what we were initially starting with. We wanted to answer the question about what that was as a function of pressure. And so now we come in and say that this is going to be equal to the fugacity coefficient of component I at the saturation conditions, Pi sat, and the Poynting factor. And I'm going to leave that in terms of the integral because I like to remind myself that this is indeed an integral that we're solving here, and that the integrated form is indeed an approximation. All right, so this is our fugacity that we were looking for, right? That we had broken out into our 3 ratios. We had one of those ratios was just unity. The other one was the saturation or the fugacity coefficient at saturation conditions. We have the Pi sat that's hanging around from our identity that we set up, and we have the Poynting factor, which was our 3rd ratio in that expression. And so if we go back then and put this in, we can come back to our equilibrium expression, which is where we started in this whole discussion. And we see that we get a total expression that's going to look something like this. All right, so this is our connection that we're going to be working with in terms of thinking about how we connect the equilibrium criterion to the measurable properties, right? So this is a big equation. There's a lot of things going on here, but right away we can notice that under a particular set of simplifying conditions that this expression is going to start to look not so unfamiliar at all, right? If we think about the limiting case where we have an ideal solution and an ideal gas, then we could come in and say that the fugacity coefficient for the ideal gas goes to unity. For an ideal solution, the activity coefficient for the liquid phase would go to unity. Our ideal gas situation tells us that this fugacity coefficient is going to go to unity. And we said that the Poynting factor is often very, very close to unity due to the fact that the argument is often very small. And so we'll make the assumption that the Poynting factor is negligible as well. So this whole term goes to unity. And if we come through and collect everything back up after making those assumptions of ideal gas, ideal solution, and Poynting factor is negligible, then this should give us a result that should look somewhat familiar, in that we simply recover the expression for Raoult's law. So again, there are a number of different ways that we can get there, and we could have started, for example, at Raoult's law and added in all these correction factors. I like to go from the most general expression, which is what we have here in the blue box, down to something like Raoult's law by making assumptions that are appropriate for the system. And so I'm going to encourage everybody throughout the semester, as we're thinking about things, to really focus in on starting from the most general place we can start, and then convince yourself and justify to yourself that assumptions are reasonable in order to simplify the math down to something that's a little bit more workable. And so this is our step as to how we're going to look at vapor-liquid equilibrium in terms of thinking about fugacity and getting that back in terms of measurables. We'll start out by talking about some ideal VLE using Raoult's law, and eventually as we go on throughout the semester, we'll get into talking more about non-ideality and some of these other terms that we show as crossed out or going to unity in this particular limiting case. And so with that, we'll go ahead and wrap up our relationship of fugacity to measurables as it pertains to vapor-liquid equilibrium.